Alright, so we're ready to talk about surface integrals. And the idea behind a surface integral is very similar to the idea behind a line integral. So recall that when we had a line integral, we had a curve in space or in the plane. And what we did is we broke this line into little pieces. And each one of these pieces we called a line element. We called it ds. And then what we did is we took some function, whether that was a vector field or a scalar field, and we added up the function values along these little pieces of the curve and then added them all up, and we called that a line integral. But remember that the most important part of a line integral, or at least the initial part, was that we needed to give a parameterization of the curve. And so that's going to be the same thing we're doing with the surface in space. So suppose that I have some surface in three-dimensional space. And what I'm going to do is I'm going to break it up into small pieces like this. And now I can think about either a vector field or a scalar field defined over this region, this little surface. And what I'm going to do is I'm going to break it up into these small pieces, d sigma, that I'm going to call surface elements. And then I'm going to add up the values of the functions on all of these surface elements. And that's going to be a double integral. It's going to turn out. But what we need to do, just like with a line integral, we needed to parameterize the curve. We need to parameterize the surface before we can do a surface integral. So how do we do that? Well, a parameterization of a surface, and we'll call the surface capital S, looks like this. Well, it's just like a parameterization of a curve. It's a vector valued function. But this time we're going to have two parameters, because inherently a surface is a two-dimensional object, whereas a curve is a one-dimensional object. And so we'll have still three component functions, and each one of the component functions will depend on both of the parameters, s and t. And again, these component functions will assume that they have continuous partial derivatives. Notice that we really need to specify partial derivatives because all of the component functions are functions of more than one variable, of two variables specifically. And so s and t, these coordinate pairs, will live in some region inside the st plane. And so this will be a region that will act as our area region when we actually do the integration over the surface. But this is a typical parameterization of a curve, what it would look like. And what we can think about is, if this was a rectangle in the st plane, what we're doing is basically taking a small little square and stretching it out as a surface in space, like this. So this is what our parameterization is doing, is taking a small little square and stretching it out into space. And so fundamentally, we're going to be doing double integrals over this region, but somehow we're going to be composing with our parameterization. So we want to review just a couple important facts about the parameterization of a surface. So let's draw a picture. We'll have here some region that we'll call R. And this is going to be in the ST plane. And I'm drawing it as a rectangle, but of course, maybe it's not actually a rectangle. And what my parameterization is going to do is it's going to take this region, R, and it's going to turn it into a surface, like we saw before, in space. And so there's my surface in space. I can draw my trace lines here. So I can think about each one of these lines, here for the t parameter, if t is constantly equal to 1, this is being represented over here. Same thing for s. So these lines kind of represent curves that have fixed s values and fixed t values. Okay, so probably the most important property of the parameterized curve is that if I look at the partial derivatives of r as a function of s and t, so if I look at r sub s and I look at r sub t, okay, so notice that the component functions of my parameterization are functions of more than one variable. So when I go to take the derivative, I really need to specify I'm taking the partial with respect to s of all the component functions, or the partial with respect to t. But these vectors, r sub t, r sub s, and r sub t, I can actually draw what they are. So recall that when we take the partial derivative with respect to s, we're fixing a t, and we're looking at the change in the s direction. And so if I go up here in my surface, r sub s is going to point tangent to that trace. And then the same thing for r sub t. Looking at the partial with respect to t, I'm just fixing an s and looking in the t direction. And so my partial derivative is tangent to the curve in that direction. But what that means is these vectors, assuming that they're not both 0, lie in the plane that's tangent to the surface. And that's really cool because this is actually going to give us a way to figure out the tangent plane at a point on the surface. And moreover, if I look at this cross product, now of course this cross product is going to be a vector valued function itself, but at each point, this cross product of the two partial derivatives is going to be a normal vector. So this vector n, which is the cross product of those two planes, of those two vectors, is going to be normal to the plane. So if I wanted a normal vector, I could just take the cross product of the two partial derivatives of my parameterization. And that's super cool. But we can actually go a step further. So let's zoom in on my partial derivative vectors here. So here's r sub t, partial with respect to t of my parameterization. Here's the partial with respect to s. So recall that the cross product, or the magnitude of the cross product, so magnitude of rs cross rt, is actually the area of this parallelogram spanned by rs and rt. So this little area is equal to that. But that's super cool, because if I think about this little parallelogram, Now this parallelogram is really going to be in the tangent plane, but if I consider a really small parallelogram, actually this parallelogram is going to approximate a little piece of the surface really well. And so I can actually just define what I mean by a surface element, d sigma. So what I'm going to mean is I'm going to take the area of the parallelogram along in the tangent plane, and then I'm just going to multiply it by a small change in s and a small change in t. So I'm going to call that dA. And here dA, I really mean ds times dt. So a small change in s times a small change in t. And now what that's going to give me is it's going to give me a parallelogram, the area of a parallelogram lying in the tangent plane that's just a really, really small piece of the tangent plane. So it's a really good approximation to a small piece of the surface. So it really is just a small surface element. And what we see right off the bat is we have a really nice way now, if S and T live in some region R, that's acting as the domain of the parameterization of the surface, if I just integrate over all S and T, this surface element here, what I'm going to get is the surface area of the region, or of the surface, which we're going to call S. So the surface area of a parameterized surface, which we're calling S, is just, okay, well, symbolically, I'm just adding up over S all of the small surface elements of S. But what that really is it's a double integral over this region in the plane, so just a typical double integral over this region, now we're calling it S and T instead of X and Y, of the magnitude of the cross product, and then with respect to this little area element here, which is just ds and dt. So I just need to describe the domain region of my parameterization, and I can compute the surface area of a region. Or sorry, of a surface described by a region. So just like when we talked about arc length of a curve, that allowed us to pretty much immediately define what we meant by the line integral of a scalar valued function. We can just go ahead, now that we have a way to talk about surface area of a parameterized surface, we can just go ahead and talk about a surface integral of a scalar valued function. So the surface integral of f, now this will be a scalar valued function, over a surface which we'll call S, but we'll think about S as being parameterized by this vector value function with S and T living in some region in the SD plane. So this is sort of like our interval for our parameterized curve. Now we have, it's a little bit more complicated to describe the domain of a parameterized surface. It's not just an interval like it is for a parameterized curve. Yeah, so what is the surface integral? Well, it's just denoted as a double integral because it really is a generalization of a double integral. You're doing an area integral, but over not just a plane, over actually a surface that's kind of curved in space. So over that surface S of f, And then this notation really tells you what you're doing. You're just adding up the function values over those small surface elements. And since we have the parameterization, we can write it as a double integral that we actually know how to evaluate. So it's just going to be f of, now I'm going to plug in, of course, the parameterization. So again, that means for x, y, and z in my function, I'm going to plug in x of st, y of st, z of st. And then just multiply by d sigma, which, since we have parameterization, is just r sub s cross r sub t, that magnitude, and then dA, which will be ds dt. Okay, so it's just a nice generalization of both a line integral and then sort of also of a double integral, just merging those things together. And so, one thing that you can do right off the bat is talk about the mass of a region described by a parameterized surface. So if this is a density function, then what you're doing is, okay, instead of just adding up all of the little pieces of surface to get the surface area, if each little piece of surface has a mass per unit area, we can actually find the mass, just like we did for parameterized curves. Okay, so recall that we had two types of line integrals. We had the line integral over a scalar valued function, which we've already generalized and talked about the surface integral of a scalar valued function. But we would also like to talk about the second type and talk about that with respect to surface integrals, and that's the surface integral of a vector field. But before we do that, we need to talk about something that's a little subtle, and we're not going to get into a lot of detail, but we at least just want to introduce the idea. So in order to do a surface integral over a vector field, or the surface integral of a vector field, we need to be dealing with what's called oriented surfaces. And loosely what this means are surfaces with two sides. Okay, and this seems a little silly because, well, maybe you're thinking all surfaces have two sides, or maybe you're thinking, what does it mean for a surface to have one side or three sides? And so certainly most surfaces that you deal with on a regular basis have two sides. If you take a basketball, the surface of a basketball, it has an inside and an outside. If I take a piece of paper, it has a front and a back. Okay, so maybe you're starting to believe me that most surfaces do have two sides, but what about an example of a surface that does not have two sides? Well, there are examples of non-oriented surfaces, and there's a famous example, and we're not going to say much about this now, but the example is called a Mobius strip. So the Mobius strip is not oriented, since it only has one side. And this is really interesting, especially if you haven't seen this before. So how do you make a Mobius strip? Well, what you do is you take a rectangular strip of paper and you turn it once and connect the edges. Okay, so let me attempt to draw a picture. So imagine that this is your piece of paper like this. And now what I'm going to do is kind of signify that there's a turn in it like this. Okay, So here's what the Mobius strip would look like if you're looking at it, but let me show you how it came about. So I took a rectangular piece of paper and I twisted it once, so turned it into this. So I'm sort of drawing this out of order, but we take the strip of paper and we turn it. So this is step one. And then we connect the two edges. So if this is like edge one, this is edge two, we just glue them together like that. Okay, so you can see, just imagine a little ant was walking around. It would come around here, it would be on the back side, but then it would sneak around here and be on the front side and then follow around, and now I would be on the back side over here. I would be behind the strip where you couldn't see the ant, and then I would come around and I'd be on the front over here, and then I'd go through the loop and I would be on the back. And if you're having trouble visualizing this, I encourage you to just get a piece of paper and do it. But I mean, we're not going to, like I said, this is all I'm going to say about oriented surfaces. Just say that, first of all, we need to deal with oriented surfaces to do surface integrals of vector fields, and we want to rule out things like this Mobius strip that is not oriented because it only has one side. Okay, so now let's say that we have a vector field. And this will be a vector field in space. So we have x, y, z. And what else do we have? We have, well, just like we had a oriented curve, we need an oriented surface. We talked about what that means. And so we'll call the surface S, but we want to assume that we have a parameterization. So the parameterization is going to look like R of ST, and S and T live in some region in the ST plane. So maybe it's just a square, or maybe it's a little bit more complicated, but that's the idea. So we have a vector field, oriented surface. Here we go. The line integral, sorry, not the line integral, the surface integral of the vector field over S is, okay, so it's going to be a double integral because it's just naturally a two-dimensional object, and it really is generalizing the idea of a double integral. Okay, so we'll have our vector field, and just like with a line integral, we want to take the component of the vector field that lies in a certain direction. And so let me draw a sample oriented surface like this. And we'll put in some surface elements just so we can see. And so remember that this surface is oriented. It has a front and a back. So you can think about this has a top and a bottom. And so we're going to have to pick an orientation. Just like with the curve, with a line integral, we have to pick a direction that the particle's moving. So here, I'm going to pick, well, a normal direction. And we'll explain what this means physically in a second. But what I'm going to do is at each one of these surface elements, I'm going to find a normal direction, and I'm going to project F onto a unit vector in the normal direction. And then I'm going to add up all of those contributions over all of the various surface elements. Okay? So this is exactly analogous to the flux integral in the plane. Because remember, a flux integral, we were measuring the amount of the field that was passing out of the curve. Well, what we're doing here is we're actually adding up the amount of the field that's passing out of the surface. So this really is a flux integral. But here by flux we mean a two-dimensional flux, so flux passing out of a surface. So the amount of water passing through a particular area or a particular surface, or an electric field passing over the surface of a cylinder, something like that. How much of the field is passing perpendicular across the surface? So that's the idea. And again, this is just notation, but since the surface is parameterized, we can actually be a little bit more specific about what we mean. What we're really doing is we're integrating over a region in the ST plane that we called R. Now, something similar is going to happen when we plug in the normal direction. So the normal direction, what is that? Well, what we can do is we can take this vector that we know is in the normal direction, divide by its length, and there we go. So there's our normal vector. But notice that d sigma actually has a factor of the magnitude of this cross product as well. So similarly to line integrals, the complicated magnitude factor is going to cancel. So what's going to be left is we're going to be looking at the vector field. Of course, we want to evaluate at the parameterization. So plug in x of st, y of st, z of st, etc. And then we dot with, well, the normal vector. And now not the unit normal vector, just the vector that we know is normal. So the cross product of the two partial derivatives of our parameterization. And then we just put in dA. And this just becomes, the integrand is just a scalar valued function of s and t. And we're doing a double integral. So it really is just a double integral, but we're just accounting for the fact that we're living on a surface in space. Just like a line integral was just a single integral, but we are accounting for the fact that we are living on a curve in space or in the plane. Okay, so in the first example, we're just going to get our hands dirty and do a couple of parameterizations of a few pretty common surfaces that you may see in space. So the first one is the sphere. And now I'm going to cheat a little bit and say that, well, we really actually have already parameterized the sphere when we talked about spherical coordinates. So spherical coordinates more or less give a parameterization of the sphere in terms of the angles. So the angle phi and the angle theta. So for the sphere, what we can do is we can actually just use spherical coordinates. And so now this is a sphere of radius 1. So that's just going to make rho equal 1. But what is x in spherical coordinates? Well, it's rho, which is 1, times sine of phi, and then cosine of theta. Okay, so I guess really here, if I want my parameterization to be in terms of s and t, I need to call one of these variables s and one of them t. So that was just a reminder, we're really thinking about phi and theta, so let's just say that we have sine of s and cosine of t. And then for y, we have sine of s, or sine of phi, really, and then sine of t. And then for z, we just have cosine of s, like that. So that's the parameterization. Now we need to give the range. So where do these st points live? This is what's really important. So they live in a rectangle. So for s, this is really like the phi variable. So that's going from 0 to pi. And then for t, that's like theta. That's going from 0 to 2 pi. And so you see, as s and t vary in this rectangle, we're really just getting points on the sphere. Okay, so the next one is the side of a cylinder of radius 1 and height 1. So this looks something like this. We're going to kind of cheat again. I mean, it's not really cheating. We're just using what we know. And think about, well, what is a cylinder? In 2 dimensions, it's really just a circle. So in the x and y direction, I can just think, well, I'm living on a circle of radius 1. And so if I put that in, what does that mean? Well, the x component I can just say is cosine of t. And notice that it doesn't matter which parameter I put where. You know, I could have used s for the angle, kind of along the unit circle. But I'm just using t, it doesn't matter. And so y, I want to be sine t. Okay, so x and y, that's just, you know, the unit circle, parameterized. And then what about for the z component? Well, the z component is just increasing constantly from 0 to 1 because it has height 1. So I'm just going to put s here, like that. And here, s, t, so s goes, say, from 0 to 1, because I'm just thinking about s as the height going up along the cylinder. So this will be 0 to 1, and then crossed with, well, I'm going all the way around the circle of radius 1, so that's 0 to 2 pi. Okay. Cool. So now, the last one, we have a cone. And this is a little bit trickier, I'll say. But a cone is sort of like a cylinder. And I want to think about, you know, if this is the z direction increasing like this, the cross sections of the cone really are just circles. But now the radius of the circle is going to depend on sort of the z coordinate, or the height. So if I let s be the height, so you see, like, if this is s equals 1 at the top and s equals 0 at the bottom, when s is 0, the radius is 0, and when s is 1, the radius is 1, and then I'm just increasing kind of in one-to-one correspondence between. So my parameterization, instead of just being cosine t sine t, is going to be s times cosine t and s times sine t, and then just s for the z component. So you see that what's going to happen is s goes to 0, the radius of the circle is going to get smaller, but in a one-to-one correspondence. I mean, if the radius and height were different, I would kind of have to account for how the radius changed as a function of the height of the cylinder. But this is what I have. And this is again for s and t in the same domain. S is just going from 0 to 1, and then t is going from 0 to 2 pi. Okay, so that's just 3 examples of commonly parameterized surfaces in space. Okay, so this is a really interesting problem, because finding the surface area of the side of a cone is not something that I would consider to be common knowledge. It's not like the area of the circle. I would expect more people to be able to tell me what the area of the circle is as opposed to the surface area of a cone. And so just to be clear here, I only want the area of the side. So I don't really care about the bottom. I know the bottom is just going to be pi r squared. And then I have a height. Okay, and then the slant height is really the distance measured along the slant. So if we call that not S, we'll call it L, like that. Okay, and again, I only want really the surface, the side surface right here. Okay, so what we can do is we can parameterize the surface and just plug it in the surface area formula. But I want to be a little careful here, because r is the radius and L is the slant height. So what I can think about, if I actually draw this in space, so if I let this be the z-axis right here, then maybe I have my cone, looks something like this, goes around. So here's R up at the top, and then I have a height, I'll just call the height h. And notice that I'm not labeling my slant height, but we'll see how that comes in a second. But what I really want to notice is that if I call this the radius of the circle, so the radius of the circle is increasing, the radius of the circle, or rather, the z-coordinate, if I look at this line, varies as a function of r by this slope h over r. So z is really h over big R times little r. Now little r is the variable. Okay, so that's just saying that as z increases, the radius of these circles is going to increase by this factor. Okay, looks good. So now I can give a parameterization of this cone right here. And so let's think about what that was. We actually just found it in the first example, but I do need to account for actually the fact that z is varying a little bit differently with the radius. So I know that I'm going to have s cosine t, s sine t, but the z-coordinate is varying with the radius in this way. And so I'm really thinking about s as being the height right here. So z is h over r, little r times h over big R times little r. But my parameter s is really acting as my height, right, is really my z-coordinate. So really, my z-coordinate is going to be h divided by r, and then times s. And just to kind of make this clear, think about when s is 0, the z-coordinate is 0. And when s is equal to r, like this, then the r's are going to cancel, and I'm just left with h. Okay? And actually here, so z is my vertical coordinate. What I'm really thinking about s being here is the radii of the circle. Sorry, I may have misspoke about that. S is really the radius of the circle. So this is really like my s coordinate here. That's how the radii of the circle are increasing with z. All right, so now what do we do? The most important thing we need to do is we need to find actually the magnitude of the cross product. If you recall the formula. So the partial with respect to s is just cosine t, sine t, and h over r. Okay? And then the partial with respect to t is minus s sine t, s cosine t, and 0. And I guess the other thing I need to do is I need to actually write the domain of s and t. So s, we said, was the radii of the circles as the cone increased. So that's going from 0. The largest radius is r. And then the angle t is going from 0 to 2 pi. Okay, so that's going to help when we actually do the double integral. And so let's first find the cross product. Okay, and so recall that the x component, I'm just looking here, so I'm going to get basically this, negative of this times this, so hs over r, and then cosine t. Then we'll block that out, and then this is going to be, well, this minus this, but it's negative, so hs over r sine t. And then over here, we have s cosine squared t minus negative, so plus s sine squared t, but that's just going to give me s. All right. And now if we look at the magnitude of this cross product, then we just square all the components. But notice that this is just going to be this squared times cosine squared plus this squared times sine squared. So this is going to be the square root of hs over r all squared, like that. Okay, and then plus s squared, like that. So what can we do? Well, I can factor out an s, and I can notice that s is positive, and I can factor out, let's see, a 1 over r, so I'll be left with s over r, and then square root of h squared plus r squared. So just, put that back under the square root, and you'll see you'll get the same thing here. But look at the square root of h squared plus r squared. This is h coming down right here. Here's r. We have a right triangle. Notice that h squared plus r squared is l squared. So that means the square root of h squared plus r squared is just l. So this is s over r times l. All right, so now to do the surface integral, to find the surface area, that's just the double integral, so 0 to 2 pi for t, and then 0 to big R for s, of this function, s over r times l, and then we have ds dt. But look what happens. So integrate with respect to s, we get s squared over 2, so that becomes r squared over 2, which is in other words, just r over 2 when we divide by r. So this is 0 to 2 pi of just r over 2 times L, and then, of course, dt. But then, we integrate with respect to dt, we just end up multiplying by 2 pi. So what do we get? We get pi r L, which is exactly what we were supposed to get. So there you go. Now, if we wanted the surface area of the entire cone, we would just add the bottom, which would be pi r squared. All right, so we want to find the mass of the hemispherical shell of radius 1. Okay, so what is the mass? Well, let's write our favorite equation. So the mass is just going to be the sum over this surface, the hemispherical shell, of all the mass elements. But what is a mass element? Well, really, I'm doing a double integral over the surface of the density times a small surface element, d sigma. All right, so now all that's left to do, most of the work, is in the parameterization of the surface. But we already know the parameterization of the sphere, so I just need to take half of it. So I can use this parameterization. So I'll think about S as being phi, so that'll be sine of S cosine t, and then sine of S sine of t, and cosine of S for z. Okay, and now let's take some derivatives. So we'll take the derivative with respect to S, and that'll be cosine of S cosine of t, and then we'll have cosine of S again, now sine of t, and then negative sine of S. And then our t is going to be, well, we're going to get negative sine S sine t, and then sine of S cosine of t, and then finally 0, because the z component doesn't depend on t. All right, so what is the cross product? Well, let's see. Let's find the cross product first. So RS cross RT. So we'll ignore these first and we'll do this minus this times this. And so that's going to be sine squared S cosine t. Okay, and then the y component is going to be this minus this minus this minus this times this. But it's going to be negative, so looks like we have 3 negatives. So it's going to be negative because we're subtracting, but then it's going to be positive. So this should be sine squared S sine t. And then what about the z coordinate? We're going to have, looks like cosine S, sine S, cosine t, and then cosine t squared, actually. Okay, so we'll have cosine S sine S cosine squared, and then minus, but it's going to be plus cosine S okay, sine s, the same thing, but with sine squared t. So that's just going to actually give me a 1 here. So we're just left with cosine s, sine s. And again, that's because we get the same thing, but with the cosine squared, and then the same thing plus with the sine squared. And there we go. So what's the magnitude here? Well, I'm going to square both of these and add them, and I'm going to have cosine squared t, sine squared t. So it looks like I have just sine now to the fourth, should be square root. It's going to be the square root of sine to the fourth s. Okay, and then plus this squared, which is going to be cosine squared s times sine squared s. But look at this. This is sine squared s times sine squared s, and this is cosine squared s times sine squared s. So I have a sine squared s plus cosine squared s, which gives me a 1, and so I'm just left with the square root of sine squared s, which if you recall, what's my range for s? It's between 0 and pi. So it's actually going to be, it's between 0 and pi over 2. So I didn't actually write the range here, but let's go ahead and, because this is going to be important because we're taking the square root. So if we know that this is always positive, we can just remove the square root. So this is really living in s is going from 0 to pi over 2 because it's the hemispherical shell, and then cross 0 to 2 pi. So I really can say that this is just sine of s, like that. Okay, well that was a lot, but that's most of the work. So what this ends up being is the integral. So t goes from 0 to 2 pi, s goes from 0 to pi over 2 of, okay, we have a sine s that's coming from the d sigma, and then this is 1 minus z, but z is just cosine s. So this is 1 minus cosine s times sine of s. And this is going to be dA, but dA is just ds dt. Okay, well this is just a nice substitution problem. I can just let u be cosine, and then I just get minus sine ds, so I'm going to get a negative sign, 0 to 2 pi. I'm letting u be cosine s, so that's going to be 1 to 0, and then this is just going to be 1 minus u du, doing the u substitution, dt, okay. And so what do we get? This looks like, well, we get a 2 pi, and then this is just going to be, I can switch the limit, the order of the limits here with the negative, and so if I can just skip a few steps, I'll have u minus u squared over 2 evaluated from 0 to 1, but that's just going to be 1/2, and so the final answer is pi. I'll let you work through the details. I know I did that kind of fast. So that's the mass of this hemispherical shell. Alrighty, so here we're going to do a surface integral of a vector field over a curve. And as you know, the most important thing to do here is to parameterize the curve. So actually here it's relatively easy because I can write z as a function of x and y. What I can do is I can just let x be s and y be t. And so my parameterization is just going to be s t, and then 1 minus s minus t. Okay, so this is something that's important to remember, that a lot of times when you're parameterizing a surface, if that surface is actually coming from a function of x and y, it's really easy to parameterize. Same thing for a curve. If the curve actually is just a function of x, y is a function of x, it's pretty straightforward to parameterize. So that's what we have here. And now, what we do need to be careful of, so recall that our region looks something like this. So it's in the first octant, and we have this plane that passes through 1 on all of the coordinate axes. And so if I look down in the xy plane, the projection down there is actually a triangle. And so if I think about fixing an x value or an s value between 0 and 1 in that triangle down in the xy plane, so I can say s is between 0 and 1, but now for a fixed s, y or t is just going to go from 0 up to this line, which now remember z is 0, so the line is actually just 1 minus s. Because if I plug in 0 and solve for y, I get 1 minus x, and s is equal to x. Okay, so here's my domain of my parameterization. It's actually a triangle. And so one thing that's interesting here is that we are specifying an upward orientation. And so we're going to have to make sure that our parameterization actually has an upward orientation. But that's not so hard to do. Okay, so let's actually find the direction of the orientation. So in other words, we want to find a normal vector and show that it's actually pointing up away from the origin. And so recall that that normal vector is given by the cross product. So rs, which is 1, 0, negative 1, and rt, which is 0, 1, negative 1. And so the normal vector is going to be the cross product, which is, okay, we're going to have 0 minus negative 1, that's going to be 1. Then we have negative 1 minus 0, but it's negative because it's the y component. So 1, 1, and then for the z component, we have 1 as well. So the normal vector is actually just 1, 1, 1. And now it's a little confusing here because in general, when we do this cross product, this will actually be a function of s and t. But because we're dealing with a plane, actually the normal vector is constant. It's just constantly 1, 1, 1. And this vector points up out of the plane. So it's not towards the origin, that would be a negative orientation. It's actually pointing up out of the origin. So that's an upward orientation. Upward just meaning sort of in the general positive z direction. Okay, so now we just want to do our surface integral of this vector field. But notice what's going to happen when I do this dot product. So here's my surface S. Here I have my region R in the ST plane. So F dot with the normal direction, since the x and y coordinates of my vector field are the same, and I do the dot product, I'm just going to end up adding them together. So I'm going to get 0, which is actually really helpful because these functions are nasty. And so I can just go ahead and do this dot product here. And notice that, well, I'm going to plug in the parameterization. And again, when I take the dot product here, even if after I plug in x of st, y of st, that should actually be of st, of course. So if I plug in x of st, y of st, z of st here, this plus this is going to be 0. So I actually only have the z component when I do the dot product, which is just going to be 1 times the z component, but evaluated at the parameterization, so 1 minus s minus t. So I'm just integrating 1 minus s minus t. And now s is going from 0 to 1, t is going from 0 to 1 minus s, and this is dt ds. Okay, so this is I have a t, so that's a 1 minus s. And then here I'm going to have a ts, so that's minus s times 1 minus s. And then I have a t squared over 2, that's going to be minus 1 minus s squared over 2. Okay, so we're going to continue evaluating this integral. Of course, I need a ds here. But the first thing I'm going to do is I'm actually going to expand what we have here. So this is the integral 0 to 1, 1 minus s plus s squared minus 1/2, and then plus 2s over 2, so s, and then minus s squared over 2, which is, so minus s plus s, 1 minus 1/2 is 1/2. We have minus s, and then s squared minus s squared over 2. That's going to be plus s squared over 2 ds. And then we'll take an antiderivative. We have s over 2 minus s squared over 2 plus s cubed over 6, evaluated from 0 to 1. So it's 1/2 minus 1/2 plus a 1/6, which is 1/6. And just a reminder that our region was a triangle, and we had our vector field. And what this 1/6 represents is the flux of the field across this surface here. And so if it was water, you can just think about that's the amount of water passing through the region, or if the vector field represented an electric field, that's the electric flux over the region, etc. Yeah, so really cool, has a really nice physical interpretation, very much related to the line integral, flux integral that we did. Just it's the amount of the field passing out of the surface.